Hello. Our aim today is to provide a student with a basic understanding of how a wing produces lift. And to also show how the lift that is generated can be controlled by a pilot, to achieve desirable flight path outcomes. By that, we mean how we can manipulate the controls to change the amount of lift being produced. This has the effect of changing the direction and height of the airplane. At the end of this session you will be able to label a diagram with the parts of an airfoil producing lift. Define angle of attack and describe its relationship with lift. And state 3 ways that a pilot can control the production of lift. We need to start our learning of pressure by first understanding what static pressure is. Static is concerned with bodies at rest or forces in balance. This is often contrasted with dynamic. Static means acting as weight but not moving. So static for our requirements can be taken to mean it's not moving. We can see the way air is acting as a static weight by the arrows. They show the force on the airfoil from the surrounding air while at rest and not moving. Even on an object in motion, on the rear side indicated by the arrows, there is only static pressure. There's no movement or motion to the air that's traveling behind the ball. That air behind the ball changes pressure with changes to weather, altitude and temperature. But not because of the movement. We have a change of pressure on the right side of the ball, which is caused by the force of the opposing air. Like putting your hand out of the window in a car. A very predictable and measurable relationship exists between static pressure and the energy of motion we just mentioned. This relationship can be used to our advantage as pilots. If we take a single air molecule, and still air, when there's no wind, we can see that the static pressure is caused by the vibrating air molecules impacting against the surface. Here's where we get to look at the energy of motion. When we introduce motion to the air, we now have two forces. Static pressure, and the energy of motion. This creates a vector. A vector is a name for something that has both force and direction. Our vector has both static pressure, which is acting as the force against the surface, and energy of motion, which is acting as the direction. As an important note, it's the airflow which always acts relative to the surface. The airflow next to the car you're traveling in may not be moving. But when you drive through that air, it's acting relative to the movement of the car. So it's the car that's moving, but we actually say the air is moving. When we increase the speed of the airflow, we can see this relationship in play. Because we can now see that the energy of motion increases but the static pressure now reduces. So the faster the airflow, which we are calling the energy of motion, the lower the effect of the static pressure at the surface. Bernoulli's theorem has been used for many years to explain how a wing creates lift. It is not the only theory used to explain this phenomena, but as it is still most widely used in aviation exams, we will cover it here. Remembering what we just learned about static pressure, let's see how that relates to the production of lift. His theorem states, within a horizontal flow of fluid, points of higher fluid speed will have less pressure than points of slower fluid speed. The fluid he's referring to for our purposes is air, as air is indeed classed as a fluid. A venturi is a cylinder, exactly like you see here, which has a decrease in the size of the cylinder in the middle. Let's take a particle, a molecule, same thing, of air. It will enter the venturi from our left side. It will get to the narrowing in the middle. If it is to pass through the narrowed middle with the same amount of air as when in the left side, it will need to speed up to achieve this. Remember, that need for the air to speed up is to get the same volume of air through the smaller middle as went through the opening. We've now got our indicator to show the speed of the airflow, and our gauge to show our air pressure, which is on the right. And our air molecule with all its friends trying to enter the venturi, is on the left. As our friends get going, We can see the constant airspeed and constant air pressure. As it nears the narrowing, it's going to speed up. The pressure drops as it speeds up, and as it reaches the other side, the airspeed decreases due to the larger cylinder, and the pressure increases again. And it's now back to how it was before it reached the narrowing. It's the very same relationship between airspeed and pressure that we were looking at. So this is all fun, but the question we need to answer is, what causes lift? And to explain that, we can turn the venturi into a cross-section of an airfoil. This airfoil is now our wing. The different shapes of the upper and lower surfaces lead to differences in the relative speed of air flowing over them. The air separates as it reaches the front of the wing. Part of it goes over the top, and part of it goes underneath the wing. The theory is that the air traveling over the top of the wing has to travel further than the air underneath the wing. This is due to the lump on top of the wing. As the air flows over the top of the wing, we produce a low pressure due to the airflow having to speed up. Once again, it speeds up due to the air on the top and the bottom having to take the same amount of time to get to the rear of the wing. Theoretically, the air parts at the front of the wing, and the top has to travel faster to meet the bottom flow at the rear of the wing at the same time. The word velocity can be used to describe our vector. Velocity means the speed something is traveling in a given direction. So a greater velocity would mean a greater speed. With an air velocity increase, static pressure decreases, resulting in a static pressure differential above and below the wing. We now have a lower pressure on top of the wing, due to the increased airspeed. And we have a higher pressure below the wing, as it hasn't really had to change its speed, or to use another word, its velocity. That is how lift is produced. An airfoil is a basic structure of a wing. Now that you're familiar with what an airfoil is, let's further define its parts and the role each part plays in the production of lift. The airfoil is a cross-section of a wing, and it has some parts we really need to know about and understand. The thicker end is called the leading edge. It's the front side that travels into the wind first. The trailing edge is on the other side and will be the last part of the wing to have contact with the airflow. When we join the middle of the leading edge to the middle of the trailing edge, we get a very important line. That line is called the chord line. The chord line gives us a view of the airfoil, and how much camber, or curve, is above and below that line. And how much camber is above and below that line is what affects the lift we produce. Okay. Now, the direction of the airflow with respect to the wing direction is known as the relative airflow. Relative airflow is always parallel with, and directly opposite in direction to the aircraft's flight path. We can start to build these pieces together. The angle of attack is the angle between the relative airflow and a reference line on the airplane or wing, such as the chord line. In practice, a pilot will control the amount of lift being produced through either the airspeed, which is controlled by the power being applied, and through the angle of attack. The angle of attack is controlled by the attitude of the airplane. This is set using the controls. Lift is one of the four main forces acting on an aircraft. On a fixed-wing aircraft, an airplane, it's defined as an upwards force created by the effective airflow as it passes over and under the wing. Lift acts in a direction perpendicular, at 90 degrees, to the direction the air is moving, as you can see with the green line pointing at 90 degrees to the relative airflow. Drag is another of the four forces acting on an airplane in flight. It's an aerodynamic force on a body, acting parallel and opposite to the relative wind. These two forces create what we call the total reaction. This is called the resultant, as it's the result of all the aerodynamic forces acting on the wing or airfoil section, and it acts through what we call the center of pressure. The center of pressure is a point along the wing chord line, where the lift is considered to be concentrated. In actuality, the wing produces lift and drag at countless numbers of points along the wing. The center of pressure is the average point used to show the result of all those points. We've already mentioned at times that the amount of lift which is created is able to be changed. So let's look at the factors that affect lift. The factors that affect lift are firstly, angle of attack. An increase in angle of attack will increase the lift being generated. If we start with a conservative 4-degree angle, and then increase that angle to say, 10 degrees, you can see that the lift produced increases. However, we can only increase lift in this way up to a certain point. The reason for that is called a stall. It's an aerodynamic condition in which the angle of attack becomes so steep, the air can no longer flow smoothly over the airfoil. You can see in this diagram in the yellow line, that the lift produced reaches a certain point, and then declines rapidly. That is what a stall is. It's a rapid decrease in the amount of lift being produced. The second factor affecting lift is airspeed. That's because the higher the air velocity, which is to say airspeed, the more energy it can impart on a surface. Speed is simply, what distance does it travel in a given amount of time? So if our wing travels a further distance in the same amount of time, it will have passed through a faster airflow, energy of motion, which will create a lower static pressure. This, as you now know, creates more lift. Let's go back to camber now. We spoke of it briefly before. It's the amount of curve in an airfoil, either above the chord line or below it. A low camber wing would have a smaller curve, and a higher camber wing would have a higher camber or curve. Different airplanes have different needs in regard to camber. It's an immensely large topic, too large for the scope of these lessons. One way we can control the amount of camber is through the position of the ailerons. These are the control surfaces on the trailing side of the wings which move up and down. These are discussed in much more detail in further lessons and are of the utmost importance to controlling any airplane. The air density is another factor affecting lift. Temperature and pressure both affect the air's density, and are covered in great detail in further lessons. By air density, we mean how many particles of air are in a certain space. The more air molecules, or particles in that space, the more dense with air it is. The worst options, and the combination which creates the least dense air, would be a high altitude, and a hot temperature. So a hot summer's day at a high altitude airport would be the least desirable air, as it is less dense and has less particles in a given space. That means less air flowing over the wing, and creating less lift. Another important factor would be the area of the wing itself. It goes to say that a jumbo aircraft needs a jumbo wing. A smaller airplane doesn't need a jumbo wing because it doesn't need to produce jumbo-size lift. On the other hand, a glider has a long wing which has a fairly high wing area. This helps it to create as much lift as possible without being able to use an engine. To look at this further, moving air imparts pressure on the surface area of a wing. PSI, or pounds per square inch, is a way of measuring that pressure. The larger the area, the more total pressure the area has. And that's because, looking at the diagram, the larger the area of the wing, the more surface of the wing is in contact with the airflow. So there you have the factors that affect the amount of lift that's created. It's very important to a pilot, as the amount of lift produced determines the performance of the airplane. This performance determines if we can land or take off in certain conditions. It also affects the speed we can fly, as well as how high we can climb. So the question then, is what can we as pilots control? Really, we can only control the angle of attack and the airspeed. To a degree, we can change the camber and wing area with flap positions, and the camber with control deflections. But, they are specialized usage and will be discussed in further lessons. Here's the relationship of angle of attack to airspeed. This is possibly the most important relationship to good flight control of an airplane. This relationship exists from the smallest to the largest airplanes. If you can understand it and apply it well, from early on, you'll be well on your way to being a competent pilot. A misunderstanding, or not giving this relationship the correct importance, has been the ruin of many a student, and even advanced pilot. The relationship is simply, the higher a given airspeed being produced, the lower the angle of attack needed, to maintain level flight. The reverse is true also. The lower the airspeed, the higher the angle of attack required, to maintain level flight. The diagram on screen shows this. On the left side of the rectangle, it shows the upper triangle, which is angle of attack, is higher. The lower triangle, the airspeed, is lower. Move to the center of the rectangle, and both angle of attack and airspeed are equal. Move to the right of the rectangle, and the upper triangle, the angle of attack, is lower. The lower triangle, the airspeed, is higher. What we can take from this is that any change to airspeed requires a change to angle of attack to maintain level flight. And vice versa. Nothing you ever learn is valuable if you can't use it. Let's have a look at this in practice. An airplane flies along at a fast speed. The angle of attack required to maintain level flight is small. An airplane flies along at a slower speed. The angle of attack required to maintain level flight is larger. Anytime you disobey this rule, you will be creating less lift. Anytime you create less lift, you are unable to maintain level flight. Which is to say you will start to descend. Well done on getting this far. Let's summarize what we've discussed in this lesson. When air flows over a surface, static pressure is reduced over that surface. The amount that static pressure is reduced varies with the speed of the airflow. Remember, the faster the airflow, the lower the static pressure. And, a pilot can use controls to manipulate changes in static pressure to direct the flight path of an airplane. Let's check our understanding, and make sure you can use what you've learned to build on your knowledge. Firstly, label a diagram of a typical airfoil. Pause this lesson and make sure you can answer this without prompting. If you do need prompting, make sure you watch again until you know them well. Okay, great. Next, define angle of attack and describe its relationship with lift. The angle of attack was the angle between the relative airflow and the chord line of the airfoil. Its relationship with lift is that the greater the angle of attack, the greater the lift produced. Number 3, state 3 ways the pilot can control the production of lift. These were by controlling the angle of attack, the airspeed, and to a lesser degree, by using flaps.